Matrix is the most important element in linear algebra, which began from solving linear equation systems. We are going to explore how matrix is used to solve linear equation systems in this video. We've learned in primary school that to solve a linear equation system, we need to eliminate the number of unknowns in an equation. When only one unknown is left in the equation, the solution value of that unknown can be obtained after we adjust its coefficient to be 1. In this example, we make the coefficient of the unknown x in the first equation to be 1. The second step is to eliminate the unknown x in the second and the third equations, after which we get an updated equation system. Similarly, we make the coefficient of y in the second equation to be 1. Then eliminate y from the other two equations. The same process is performed to eliminate z from the first two equations, after which we get the final solution set that we want to get. What if we take out the unknowns from the equation systems? As x, y, or z, adjust the names of the unknowns, which can be replaced by a, b, or c if you want. We can rewrite the equation system in a form called Augmented Matrix after the unknowns are taken out. Does this look a little bit cleaner? Furthermore, we can keep the coefficients of the unknowns only in the form of the coefficient matrix. Let's compare the first step. Adjusting the coefficient of the unknown x in equation R1 to be 1 and eliminate x from the other two equations. The operation on the augmented matrix is exactly the same with operations on equation system, except that it looks cleaner. Simply repeat the whole process. We can get a final augmented matrix with a unique 1 in each column and the rest in the same column to be 0. The right part of the augmented matrix are the final solutions of the unknowns. Let's recap what we did with the augmented matrix and try to find some useful patterns. First of all, we make one number in a row to be 1, usually the first number in the first row, the second number in the second row, and so forth. We achieve this through multiplying a non-zero real number to this row. Then, we adjust the other numbers in the same columns to be 0, which is achieved by adding a multiple of a row to another row. Eventually, we get a row-reduced echelon form of an augmented matrix, which only has a 1 in each column, and the position of the 1 shifts right with the row number increased. This operation on augmented matrix is described by Gauss and Jordan first, and is called Gauss-Jordan elimination. We will talk a little bit more about row-reduced echelon form in the coming videos. Please stay tuned and see you next time.